So we are going to look at the last thing, namely the series with alternating terms. So let's go ahead. So you'll have the alternating series in this way. Summation -1 power n minus 1 un. So you'll get the first term as even because raised to power 0, and then sorry, the first term as positive, the second term as negative, and so on. So this is a series of alternating terms. And the result which we use is called as the Leibniz theorem for alternating series. So let me state the theorem first and then look at some problems. So till the last class, we only dealt with series of positive terms. Now I'm going to give you examples. For example, even before I state this, let's give an example. Suppose we have something like this. I said the first term is positive, the second term is negative, the 3/2 plus 4/3 minus 5/4 and so on. So one gets puzzled as to what should we do with this kind of a series where you have alternatingly negative and positive terms, and we have to decide whether this is convergent or divergent. So the Leibniz theorem, which I alluded to earlier, is the following. So let summation -1 power n minus 1 un. By default, we always have the series starting from n equal to 1 to infinity. Let this be like this. And this converges so let me state this theorem. This alternating series converges if this criteria is satisfied, and if it's not satisfied, it does not converge. So what is the criteria? The preceding term compared to the next term should always be greater. That is, un is greater than un plus 1 for all n. And the second thing is limit of this general term un is 0. So we can see some examples also on this, but if these two are satisfied, then we can declare that it is convergent, or else it is not convergent. Remember, we don't say divergent because it's alternating series, so who knows, it may be oscillatory also. So we don't say if this fails, it is divergent, but we say if this this criteria fails, it is for sure not convergent. So let's look at an example. The same example. Well, let's take 2 minus 3/2 plus 4/3 minus 5/4 plus 6/5 and so on. So how does it look like? This is the general term here is n plus 1 by n with a -1 power. So this general term can be written as minus 1 power n minus 1 term times n plus 1 by n. See here? So if you take n is equal to 1, you have 2 by 1. So we realize this term. If you take n equal to 2, you have 3 by 2, we realize this term. If you take n equal to 3, 4 by 3, we realize this term because the signs are taken care of by this. Okay, so we have this summation minus 1 power n minus 1 times un is this. So which means your un in the given example is n plus 1 by n. Expression for un as per this format is n plus 1 by n. So let's check this first criteria. What is happening to un plus 1 minus un is nothing but n plus 2 by n plus 1. I'm just adding and I'm putting n plus 1 in the place of n minus n plus 1 by n. And this turns out that it is n minus n plus 1 whole square. Turns out that it is minus 1. Turns out that it is minus 1 by n square plus n. So, do you see for all n, because n is always taken by the natural numbers, so this is 0, less than 0 for all n, right? So what does that mean? That the difference between the next term and the preceding term is negative, means the next term is less than the first term. So your criteria 1 is satisfied. Let's look at the criteria 2. Limit un as n tends to infinity is limit n plus 1 by n as n tends to infinity, which is n 1 plus 1 by n by n. I'll have to, I just simplified the expression. Now take limit as n tends to infinity of this. So as n tends to infinity, this term is 0, 1 by n goes to 0. So this is eventually 1. And let's see the criteria 2. It wants the limit of un to go to 0, but it's not going here. So limit of un as n tends to infinity is not equal to 0. Hence, given alternating series is not convergent. Okay. So the question here is, if you are asked, state the Leibniz criteria, Leibniz rule for checking the nature of an alternating series, then you say that this is the rule. The rule says that if this format of alternating series satisfies the rule, un plus 1 is less than un for all n, and limit un as n tends to infinity is 0, then it converges. Else, we can just say it does not converge. We cannot definitively say that it diverges, but we can say that it does not converge. Right. So let's see a quick second example. Test by using Leibniz criteria. 1 by 2 cube minus 1 by 3 cube into 1 plus 2 plus 1 by 4 cube into 1 plus 2 plus 3 and so on. It's clear. If your summation Tn is given in this way, let's say, I'm conscious about the notation because the general format I take minus 1 power n minus 1 times un. So here I'm just saying your summation Tn is of this form. So now if I want to write it in summation minus 1 power n minus 1 un, by default, sometimes I drop this, but please note that you should have this n equal to 1 to infinity, this sum. In this format, in this format, we have un. Just observe what is happening there. What is happening there is 1 by n plus 1 the whole square. See, for first term it is 2, second term it is 3 and so on. So it is 1 by n plus 1 the whole square, and in the bracketed term is 1 plus 2 plus 3 up to n. So un is 1 by n plus 1 the whole square, and the bracketed term is 1 plus 2 plus so on up to n. So for n equal to 1, you have only 1. See here, you have only, if there is nothing, it's 1. N equal to 2, you have 1 plus 2. N equal to 3, you have 1 plus 2 plus 3. So in general, you have 1 plus 2 plus 3 up to n. This is the bracketed term, right? So now we have to check for this. So let's look at the first criteria, un plus 1 minus un. Now I'm going to write it as n plus 1 by 2 into n plus 2 the whole square minus n divided by 2 into n plus 1 the whole square. Why? Because these bracketed terms get cancelled. Okay. So, or you can check in another way. Okay. So this is your the difference between the next term and the preceding term. Let me prove it in this way. Un is 1 by n plus 1 the whole square into 1 plus 2 plus 3 up to n. So the same as 1 plus n plus 1 the whole square. Here, you know that sum of first n terms is n into n plus 1 divided by 2. So if you expand this, uh, if you expand this, you will get n plus 1 divided by 2 into n plus 2 the whole square. Okay, you will get un plus 1 as n plus 1 divided by this 2 into n plus 2 the whole square. This is your n plus 1. And your un is 1 by n plus 1 the whole square into n plus 1 by 2. So by using these two, you will get this difference. So if you subtract, so therefore un plus 1 minus un is going to be n plus 1 by 2 into n plus 2 the whole square minus n divided by 2 into n plus 1 the whole square. You can check that you cancel this n plus 1, n plus 1. So it's just n divided by 2 into n plus 1 the whole square. Okay, so we get the difference as minus n square minus n plus 1 divided by 2 into n plus 2 the whole square, n plus 1 the whole square, which is clearly again, see, for all n, even if you take n equal to 1, this is negative. As n increases, definitely this negative term is more than the positive term. Therefore, this is clearly less than 0. Therefore, un plus 1 is less than un. So first criteria, rule 1 of the level, rule 1 is true. Also look at limit un as n tends to infinity is limit n by 2n plus 1 the whole square as n tends to infinity. Let's quickly check what is happening here. This is I'll try to put it in this way, n into 2 into 1 plus 1 by n the whole square, limit as n tends to infinity. So this is clearly 1 by 1 plus 0 the whole square. So this is 1. So wait, sorry. So I think yeah, you can't get away with this n because um, I think I'm slightly mistaken here. So what is happening with this? This is limit n divided by 2 n square plus 1 plus 2n. So now so yeah, uh, even if you want to get rid of this n, in the first term there's a square, remember? So it is n plus 1 by n plus 2. Limit, I should have space here. As n tends to infinity. So now there is a n remaining in the denominator, and therefore this is going to be 0 because 1 by infinity is 0. So limit is indeed 0. Therefore, second rule is satisfied. Therefore, rule 2 is true. And hence, by Leibnitz criteria, we declare this alternating series, namely there is 1 by 2 cube plus 1 by 3 cube into 1 plus 2 plus 1 by 4 cube into 1 plus 2 plus 3 is convergent. So I close the class here.